we were discussing metric spaces in the last class. So let us recall a few things once again. Recall that a metric is a function D from x cross x to R satisfying some properties. Let us again recall those properties. First property was this, that this distance is always bigger than or equal to 0, and this is for all xy in x, and it is equal to 0 if and only if x equal to y, okay, equal to 0 if and only if x is equal to y. And second thing is what is called symmetry, that is distance between y and x is same as distance between x and y for all xy in x. And the last property which we had called triangle inequality, that is if you take 3 points, then the distance between x and z is less than or equal to distance between x and y plus distance between y and z for every x, y, z in x, okay, right. And we had said that a metric space is a pair x comma d, okay, where x is a non-empty set and d is a metric defined on S. Okay. Then we saw some examples for metric space. One example is what we saw, a discrete metric. Discrete metric can be defined on any set, and the definition is fairly simple, that the distance between any 2 points is 0 if the 2 points coincide, and if 1 if those 2 points are different. That is a trivial example, but that is an example which helps in understanding several things, and that we will see as we go ahead. Okay. Then coming to the other class of examples, we had seen that one of the major class of examples of metric spaces that are very important from the practical point of view are what are called non-linear spaces. Okay. Okay. Now here in case of non-linear space, the starting point is not an arbitrary set, but it is a vector space. Okay, X should be a vector space. So it means there is a meaning in saying the sum of the two vectors, product of a scalar and a vector, and all those things. Okay, and we have also seen that a norm on X, that is a function norm that is going from x to r, and that satisfies again 3 similar properties like this. The first property is norm of x is bigger than or equal to 0 for all x in x, and norm of x is equal to 0 if and only if x is equal to 0. Okay, and second property is norm of, okay, I may or may not have written those properties in the same order, but the point is there are 3 properties. Okay, that is alpha times x is mod alpha times norm x. This is true for every x in x and alpha in r. And finally the property what we had called triangle inequality, that takes this form, norm of x plus y is less than or equal to norm x plus norm y. This is true for every x y in x. Okay. Okay. And non-linear space is again a pair x norm, where x is a vector space and norm is a norm on it. Okay. If it is a vector space over R, we call it a real non-linear space. If it is a vector space over C, we call it a complex non-linear space. Okay. As far as these properties are concerned, 1 and 3 does not depend on what are the scalars. Okay. Only this property 2 depends on what are the scalars, and here only appropriate change will be, instead of taking here alpha in R, you have to take alpha in C. Okay. And what we have seen is that every non-linear space is a metric space. Okay. And how does it become a metric space? Taking any 2 vectors x and y, we define distance between x and y as norm y minus x. Okay, as norm y minus x. Okay, and this D is called a matrix induced by this norm. Okay. So we can say that D is called a metric induced by norm. Okay, by the norm, this norm. if this is a relationship between the norm D, see the metric D and this norm, then we say that D is a metric induced by a norm. So every norm induces a metric, okay, every norm on a vector space induces a metric, and so that gives us a big class of examples. Of course here it is very natural to ask question whether every metric is induced by some norm, okay, right, but of course that is obviously not true, because metric can be there even on an arbitrary set, okay, metric can be defined even on an arbitrary set, that need not be a vector space, okay. Even on a vector space also there can be a metric which does not come from any norm, okay, right, because if a metric is induced by a norm then it has to satisfy some extra properties, okay. What are the extra properties? Okay, since we have raised this point, let me mention here that extra property is what is called translation invariance, okay. Translation invariance, okay, that is if a metric is induced by a norm then that metric, we say that that metric is invariant under translation, okay. What is the meaning of translation? Translation means adding a fixed vector to each, okay, that is the map which takes x to x plus a, okay, that is called a translation, okay, that means you add just a fixed vector to all, okay. So suppose x goes to x plus a, y will go to y plus a, okay, then the distance between x and y should be same as distance between x plus a and y plus a, that is in this case distance between x and y, that will be same as distance between x plus a and y plus a. Why? Because this is norm of y minus x, that is norm of y plus a minus x plus a, okay, which is again same as y minus x. So if a metric is induced by a norm, that, so this is a property which is called translation invariance, okay, that is for any a distance between x and y is same as distance between x plus a and y plus a, okay. This property may or may not be true of an arbitrary metric, okay. For example, on a vector space you can also give a discrete metric, okay, that will not satisfy this property, okay, or I would say that that may or may not satisfy this property. So we cannot so given it is possible that a metric may not be induced by any norm, okay. So one way of checking that is this. Similarly something will follow from this property also, but I will not go into that discussion because that is not very important right now, okay. Let us now go to discussing various examples, that is concrete examples of metric spaces, and in particular I would say since the major class of examples are of this type, we shall discuss those examples of norm linear spaces, okay. Let us start with very well known examples. Obviously this R, okay. R itself is a metric, is a norm linear space. I would say that you take this absolute value function here, okay, right, then this absolute value function satisfies all these three properties, okay, that is something we already seen. So that is a norm linear space, hence a metric space, because and this metric that is, so the metric will be dxy given by mod y minus x, okay, okay. This metric is usually called usual metric on R, okay, okay, this is called usual metric or usual distance, okay. Now you can see that whatever we can do about R, the same thing can be done on C also. On C also you have an absolute value function, okay, so we can also talk of the absolute value of a complex number. So we can take this also, and that is also called usual metric on C, okay, that is also called usual metric on C. Why it is called usual metric? Because it is possible to define several other metrics, okay, right, it is. And so is it, for example, clear to you that suppose I have such a function d, okay, suppose I have, and suppose I define say d1 of xy as 2 times dxy, let us say, okay, then that will also satisfy all these properties, okay, that will also satisfy all. So that will be a new metric. So there is nothing unique about metrics, okay, several metrics can be defined on the same set. So but as a metric space we regard those as different metric spaces, okay, alright. Now let us continue with the examples. Now let us go to let somewhat higher dimension. Instead of talking about R, let us take R2, R3, etc., and similarly C2, C3, etc. So in general, let me talk about Rn. Okay, Rn. Okay. Now what are the elements of Rn? Rn is nothing but the Cartesian product of R with itself taken n times. So every element is ordered n tuple. Okay. So x belongs to Rn. This means x is of the form x1, x2, xn, and as you know these numbers x1, x2, xn, they are all called coordinates. Okay. Xj is the z coordinate. Right. So I will define a norm on this. In fact, what I would say is that not just one norm, but I will define what is called a family of norms. Okay. Okay. So to do that, let me just take this number p. Let us say 1 less than or equal to p less than or equal to infinity. Okay. And I will define a norm depending on this number p. Okay. Depending on this number p. Okay. Norm of x. So I will call it norm suffix p. Norm suffix p, and this is defined as follows. It is sigma j going from 1 to n mod xj raised to the power p whole to the raised to the whole thing raised to the power 1 by p.
So that should be p less than infinity, not equal.
Wait, I will come to that. Okay. So this is for this particular definition for 1 less than or equal to p less than infinity. Okay. Alright. And for p equal to infinity, we define that as maximum of mod x j equal to 1 to n. Okay. So this last norm is called norm suffix infinity. Okay. Now, and all these others are norm suffix p for 1 less than or equal to p less than strictly less than infinity. Okay. So these are called p norms or LP norms. Okay. P norms are sometimes also called LP norms. Of course, we have to prove that these are the norms. Okay. That is something we have not proved yet. Okay. But as I told you, proving that these are the norms, we have to verify these three properties. Okay. And out of these three properties, these two are very trivial. Okay. Those follow more or less immediately from the only thing that will require some work is this property 3, which is called triangle inequality. Okay. Which is called triangle inequality. Okay. Is it clear in this case also? For example, suppose we take this case. Suppose this is, it is clear that this is, each of this is bigger than or equal to 0, whatever definition you take. Okay. Suppose it is equal to 0. Okay. Then this summation is equal to 0, but it is a sum of non-negative numbers. So if that is 0, each of them must be 0. Okay. So that gives that each xj must be 0. Similarly, if the maximum of mod xj is 0, then each mod xj must be 0, so each xj must be 0. Okay. So that is easy to verify. Similarly, suppose you take alpha times x, then the coordinates are alpha x1, alpha xn. So if you put it here, that mod alpha will come outside. So second property is also very easy to verify. Okay. So what remains to verify is the third property, namely the triangle inequality. Okay. And it is that property only which requires some work. Okay. And there also you will see that it is very easy to check that also for these two cases. Okay. The case p equal to 1 and p equal to infinity. Okay. These two cases, this triangle inequality is also very easy, because for p equal to 1 what happens, let us call this norm suffix 1. Okay. Then it is nothing but sigma mod xj. Okay. Sigma mod xj. Okay. So what is norm of x plus y? Suffix 1. So this is sigma j going from 1 to n mod xj plus yj. Okay. And what is to be done after this is clear. Okay. Mod xj plus yj is less than or equal to mod xj plus mod yj. So separate the two sums and you get this, that is the right hand side will be, so continue this will be less than or equal to norm suffix 1 plus norm y suffix 1. Okay. Okay. In the similarly for the case p equal to infinity, this norm suffix infinity will be maximum of mod xj plus yj, okay, and then you can easily show that that is, since for each j mod xj plus yj is less than or equal to mod xj plus mod yj, by taking maximum of all these quantities you will be able to show that this is also true, that norm of x plus y suffix infinity is less than or equal to norm x plus norm y for p equal to infinity. So these two cases are easy, okay. What requires some non-trivial work is the case when 1 strictly less than p strictly less than infinity, okay, alright. And in this case, to prove that norm of x plus y, that means what is to prove in this case, we need to prove this norm of x plus y suffix p is less than or equal to norm x suffix p plus norm y suffix p, okay. And let me write this in the full form instead of this, okay. Okay, so what is this? It is mod xj plus yj raised to p, j going from 1 to 8, and then this whole thing raised to 1 by p. This should be less than or equal to sigma mod xj to the power p, this raised to 1 by p, plus again here same thing for yj, sigma mod yj to the power p, j going from 1 to 8 whole to the power 1 by p, okay. And this what I have written here is a very famous inequality about the real numbers. It is called Minkowski's inequality. Okay. And suppose we prove this inequality, okay, then it will follow that this is true, okay, this is true, and then from that it will follow that this is a norm, okay, it will follow that this is a norm, okay, alright. Now we will try to prove that. In proving this, okay, we have to go through some steps, okay. There are some inequalities which we require to prove this inequality, and those we will have to prove in between, okay. So for that, suppose we take, to begin with, let us say we take two numbers, a bigger than 0 and b bigger than 0, okay, and for that we also need a notion of what is called conjugate exponents, okay, conjugate exponents, okay. Conjugate exponent to this p is called an exponent, any number 1 less than 1 p less, so this p, because we are taking the power, pth power, etc. So conjugate exponent to p means what? It is again a number lying between 1 and infinity, it is again a number lying between 1 and infinity and satisfying this, that is we have these two numbers, 1 less than or equal to p less than or equal to infinity and 1 less than or equal to q less than or equal to infinity, okay. And if these two numbers satisfy this property, 1 by p plus 1 by q is equal to 1, okay, 1 by p plus 1 by q is equal to 1, okay, then p and q are called conjugate exponents of each other, okay. Most obvious case is when p and q both are 2, okay, if p is 2 and q is also 2, then this is 1, okay, that is the symmetric case, okay. So 2 is a conjugate exponent of itself, okay. So it is clear from this that if p is less than 2, q will be bigger than 2 and vice versa, okay. And by convention we take if p is 1, q is infinity, because if p is 1 this number becomes 1, so this to be satisfied q has to be infinity and vice versa. So we take 1 and infinity as the conjugate exponents of each other, okay, and for 1 less than p less than infinity it is defined by this, okay, alright. Okay, so where does that come into picture here? So it is this inequality, if you take two positive numbers then this ab is less than or equal to a to the power p divided by p plus b to the power q divided by q. Okay. This is sometimes called Young's inequality. Okay. Okay. And let me also write one more inequality. It is like this: if you take sigma mod xj yj, j going from 1 to n, sigma xj yj, then this is less than or equal to sigma mod xj to the power p. I will forget about j going from 1 to n. This j goes from 1 to n everywhere whenever I write the summations here, there is a convention. Okay. This raised to 1 by p plus, so not plus, multiplied by sigma mod yj to the power q, this whole thing raised to 1 by q. Okay, where p and q are conjugate exponents of each other. Okay. This last inequality, that is called Holder's inequality. Of course, it is, if you remember that norm suffix p is defined like this, then Minkowski's inequality is nothing but norm of x plus y is less than or equal to norm x into norm y. Okay. One can give a similar way of remembering this Holder's inequality. See, if you take the vector x as x1 x2 xn, and suppose we take y as y1 y2 yn, and suppose I write the vector xy as the vector that you obtained by just coordinate wise multiplication. Okay, right, just multiply coordinate wise and write that as a vector xy. So it will be x1 y1 x2 y2 etc xn yn. Okay, then what we have here left hand side is nothing but the one norm of xy, right. This is p norm of x and that is q norm of y. Okay. So another way of writing Holder's inequality, which is easy to remember, is this, that is norm of xy suffix 1, this is less than or equal to norm x suffix p plus norm y suffix q. Okay. And this is true for all possible p and q, where p and q are conjugate exponents of each other. Okay. All possible p and q, where p and q are conjugate exponents of each other. Okay. And from what we have seen earlier, to prove these inequalities for p equal to 1 and infinity is easy. Okay. So I will leave that case to you. For proving that for p equal to 1 and p equal to infinity, that is easy. Okay. So we shall only discuss this particular case, 1 less than p less than infinity, and so that will also imply 1 less than q less than infinity. Okay. Okay. If p lies strictly between 1 and infinity, q also lies strictly between 1 and infinity. Okay. Alright. Let us start from this first. Okay. So called Young's inequality. Okay. Is it also clear to you that if p and q both are 2, the conjugate exponents, then this becomes a well known inequality. Okay. Suppose p and q both are 2, then that simply becomes ab is less than or equal to a square plus b square by 2, right. Okay, and that is very easy to prove. Okay. Okay, a square, this is same as saying that 0 is less than or equal to a square plus b square minus 2ab. Okay. That is a square plus b square minus 2 is nothing but a minus b whole square, so that is always bigger than or equal to 0. So that case it is very easy to prove, and in fact you will see that all these inequalities will also fairly easy to prove when p and q are equal to 2. Okay. General case will involve some work. Okay. But again not very difficult. Basically we use the methods of elementary calculus, okay, to prove this inequality. That is, we take some function and show that that function increases or decreases in some intervals and take an appropriate values of t. Okay, for example, suppose I take of this function ft is equal to 1 by q plus t by p minus t to the power 1 by p. Okay. For t in R. Okay. Then okay. So look at the derivative f prime t. Okay, derivative of this will be 0, so it will be 1 by p minus derivative. Remember, 1 by p is bigger than 1. Okay, okay. So sorry, not bigger than 1, less than 1. Okay, so it 1 by p. Oh, derivative of this is 1 by minus 1 by p into t raised to 1 by p minus 1. Okay, so that is 1 by p into 1 minus t raised to 1 by p minus 1. Okay, all right. Now, okay, it is obviously 0 if t equal to 1. Okay, at other places whether it is 0 or not depends on what is this exponent 1 by p minus 1. Okay, right. Now 1 by p minus 1 is a negative exponent, right. If p is bigger than 1, 1 by p is less than 1. Okay, but of course it is basically same as saying that it is 1 by t. Okay, okay. So what it means is that for one of the cases it will be bigger than or equal to 0, and for the other case it will be less than or equal to 0. So what is the case? Tell me when it will be bigger than or equal to 0. It will be bigger than or equal to 0 if, and less than or equal to 0 if.
When t is greater than 1,
Yes,
t is greater than 1, then it is equal to 0, greater than equal to 0.
okay, if
T is greater than 1,
yes, and
yeah,
less than or equal to 0 if
t is less than 1.
t is less. In fact, here you have strict inequality actually. Okay, right. Okay, just check that. Okay, is that clear? Okay, all right. Okay, so what follows from this, that the function is 0 at t equal to 1. Okay, okay, and it is increasing for t bigger than 1 and decreasing for t less than 1. So suppose you were to draw a graph of the function, suppose this is t equal to 1. Okay, at this point the function is 0. Okay, and for t bigger than 1 it increases. Okay, and for t less than 1 it decreases. Okay, so does it follow from here that it must be bigger than or equal to 0 everywhere? Okay, okay. So what it means is that if t is bigger than or equal to 0 for all t. Okay. Then now what I will do is I will take t is equal to a by p plus b, a raised to p plus divided by b raised to q. Okay. T is equal to a raised to p divided by b raised to q. Okay. And I will use the, so for this t also f of that should be bigger than or equal to 0. Okay. So what is f of this? So f of t, okay, what will be that? It will be 1 by q plus t by p, that is a raised to p plus p into b raised to q, minus t is again, okay, a raised to p divided by b raised to q, and then this whole thing raised to 1 by p. Okay, this must be bigger than or equal to 0. Okay, now simplify this and you should get that inequality. Okay, so simplifying this, what we will get? Okay, suppose I just I take this term on the right hand side, so I can write this as, okay, right. So this will be the a to the power p whole to the power 1 by p, so this is nothing but a. Okay, numerator is nothing but a. Okay, and this is divided by b to the power q by p. Okay, then what is to be done after that is clear. You multiply whole thing by this b to the power q by p. So this will become, so when you bring it here it will become b to the power q divided by q plus a to the power p divided by p, and that is bigger than or equal to ab. Okay, and so that is what we wanted to prove. Okay, that is Young's inequality, right. Okay. Of course you can check these calculations, there is nothing much there. Okay. Yes. Okay. Now let us see how we want to prove this. Okay. Let us go to Holder's inequality. Okay. Now for Holder's inequality, okay, let me call these right hand sides this and this as alpha and beta. So suppose this is alpha and that is beta. Okay. So what is the meaning of this? It means, okay, let me write here, it means alpha is sigma mod xj to the power p whole to the power 1 by p, and sigma mod yz, so beta is this sigma mod yz to the power not p, that is q to the power q whole to the power 1 by q. Okay. Now let us first dispose of trivial case. Okay. Suppose one of them is 0, that is, say suppose alpha is 0. Okay. If alpha is 0 then all xj's are 0. Okay. Then the left hand side is 0. Okay. Then nothing is to be, right hand side is anyway a non-negative number. Okay. Right. So if alpha is 0, nothing is, it follows trivially. Similar case with beta is equal to 0. Okay. Similar case with beta is equal to 0. Okay. So if alpha is equal to 0 or beta equal to 0, this follows trivially. So we only need to consider the case when alpha and beta are both strictly positive. Okay. So let us say assume alpha bigger than 0, beta bigger than 0. Okay. So what I can say is that basically what we need to prove is this, that this sigma j going from 1 to n mod xj yj is less than or equal to alpha into beta. Okay, right, or which is same as saying that because alpha and beta both are bigger than 0, I can say that sigma mod xj yj this divided by alpha beta less than or equal to 1. This is what we want to prove. Okay. Now what I will do is that I want to apply this Young's inequality to these numbers. Okay, mod xj divided by alpha and mod yj divided by beta. Take this as a and that as b. Okay. Take this as a and that as b. Okay. Okay. Of course, I should say one more thing here. Though here I have said a greater than 0 and b greater than 0, remember that if one of them is equal to 0, this inequality is again trivial. If a is equal to 0, the left hand side is 0, so whatever is there on the right hand side, this will be still true. Okay. So I will just make a small change here, a greater than or equal to 0 and b greater than or equal to 0. Okay. Then also this inequality is true. Okay. All right. Okay. Suppose I apply this Young's inequality to this, then what do I get? I will get this sigma, see this raised to p divided by p plus this raised to q divided by q, right. Okay. So that is mod xj to the power p divided by alpha to the power p into p, right. Okay. That is the first term, a to the power p by p. What is the second term? It will be mod yj to the power q divided by q beta to the power q, right. Okay. This I can do for each j. Okay. This I can do for each j. So this is true for all j going from 1 to n. All j going from 1 to n. Okay. And then take the sum. Okay. So taking the sum, what we will get is this will be sigma mod xj into mod yj, this whole thing divided by alpha beta, that will be a left hand side, okay, that is taking sum. Okay, and what will be the right hand side? It will be sigma mod xj to the power p divided by, this will remain as it is, p alpha to the power p plus sigma mod yj to the power q divided by q beta to the power q. Okay, but this is nothing but alpha to the power p, okay, because alpha is this raised to 1 by p, okay. So this right hand side is nothing but 1 by p plus 1 by q, right, okay, and that is equal to 1. Okay, so that proves Holder's inequality. Of course, you may say that here you have mod xj into mod yj, but here we had mod xj into yj, but you see there is no difference, okay, these two things are the same, okay. So is it okay? So we have proved Holder's inequality, okay, right. So only thing remains now is to prove this Minkowski's inequality. Okay. Again we will start with the obvious point, if any one of these, okay, not any, there you have a sum, okay, there you have a sum, okay, if both of them are 0, if both of them are 0, then it means each xj is 0 and each yj is 0, and in which case the left hand side is also 0, so the inequality follows trivially, okay, inequality follows trivially, okay. So we need to consider only the case when both of them are strictly positive. Why do we have to go through such steps? Because we may need to divide by those numbers somewhere in the proof, okay. So to justify that, we must say right in the beginning that those numbers are different from 0, and since they are already non-negative, it means they are strictly bigger than 0, okay, alright. So what we can start from is this, okay, look at okay, sigma j going from 1 to n, let me say mod xj plus yj raised to the power p, let us say, okay. Remember p is strictly bigger than 1, this is the case we are considering, 1 less than p less than infinity. So I can write this as, okay, let me do it in the next step, okay. Write this as sigma j going from 1 to n mod xj plus yj into mod xj plus yj into p minus 1, okay, I can do that, right, okay, fine. Okay, now to this I want to apply Holder's inequality, okay, right. I will take these numbers as xj's and these numbers as yj's, okay, right, because we have something like this, right, we have sigma mod xj yj, right. So similarly we have sigma over j something depending on j multiplied by something depending on j, okay, right. So for this product I will now apply Holder's inequality, okay. So what follows from here? So what I should do is that for this I should raise to p, take the sum and then raise whole thing to 1 by p, okay, alright. So what is this? This is sigma over j, okay, I will forget about this 1 to n. So mod xj plus yj raised to the power p whole to the power 1 by p, okay, alright. What about this? Again sigma over j mod xj plus yj to the power p minus 1, and we have to raise this to the power q, okay, we have to raise this to the power, so it is p minus 1 into q, right, p minus 1 into q, and then this whole thing raised to 1 by q, okay, that is by applying Holder's inequality to this, okay. Do you agree with this? Okay. Now let us just look at this exponent. What is the exponent here? It is p minus 1 into q, okay. So what is that? It is PQ minus Q, okay, PQ minus Q. See, remember till now we have not used the fact that P and Q are conjugate exponents, okay, we shall use it now, okay. What is PQ minus Q? What is the relationship between P and Q? It is this, 1 by P plus 1 by Q is 1, okay. So what follows from here? It is that suppose you multiply by PQ throughout, it is P plus Q is equal to PQ, right. So this PQ minus Q is nothing but P, okay, PQ minus P is nothing but P, okay. So this exponent here is nothing but P, okay. All right. Okay. I should have done one more thing before this, okay. Okay, I will go back to this step, we will come to this step. So you see, mod xj plus yj is always less than or equal to mod xj plus mod yj, right. So I can, instead of this equality sign here itself I will take this less than or equal to, okay, right. Then I make this first term as mod xj plus mod yj, okay, and similarly the second term also as mod xj plus mod yj, then this whole thing raised to P minus 1, okay. In other words, wherever there is just xj plus yj, we will replace it by mod xj plus mod yj, okay. So this is mod xj plus mod yj raised to P, and here also mod xj plus mod yj this raised to P, okay. It is okay, there is no problem with that, right, because see earlier everywhere we had mod of xj plus yj, but we all know that mod of xj plus yj is always less than or equal to mod xj plus mod yj, okay. No, I think we have to have some more steps in. Okay, I think let us not do it in this fashion, okay. Let us say this is sigma j going from 1 to n mod xj plus mod yj into P minus 1, okay, right. And what I will do is that there is, okay, I forgot about one, there is one more step in between and then we will do what we did, okay. So this is same as sigma j going from 1 to n mod xj into sorry, okay, I think again not this way, it is mod xj plus yj into mod xj plus yj to the power P minus 1, and now I will try this. This is sigma j going from 1 to n. This is I will do it only for this first term, okay. This mod xj plus yj is less than or equal to mod xj plus mod yj, okay. So this is less than or equal to mod xj plus mod yj, and then this I will keep as it is, okay, mod of xj plus yj to the power P minus 1, okay. Then I will split this sum into 2, okay, I will split this sum into 2. So this is less than or equal to sigma j going from 1 to n mod xj into the second term is this mod xj plus yj to the power P minus 1, and then plus sigma j going from 1 to n mod yj into mod xj plus yj to the power P minus 1. Do you agree with this? Okay. alright. Now after this we apply Holder's inequality to each of these, okay. Whatever we had done earlier, these in between steps were missing in the earlier calculations, these are important, okay. So now we apply Holder's inequality, okay. So what we do is that, so suppose I apply the Holder's inequality for this first sum here, then this will be less than or equal to sigma j going from 1 to n mod xj to the power p whole thing raised to 1 by p into this second term will be sigma j going from 1 to n mod xj plus yj raised to p minus 1 into q, and then this whole thing raised to 1 by q, okay. That is for the first sum, okay. For the second sum what will happen, this will be instead of mod xj to the power p 1 by, it will be, okay. So the plus sigma j going from 1 to n mod yj to the power p, then whole thing to the power 1 by p, and the second term will be the same, right. Second term will be mod xj plus yj to the power p minus 1 into q, okay, and then the whole to the power 1 by q, okay, alright, okay. Now you see that this second term, there are two things to be noticed, okay. Which one thing which we have already noticed, that this is the thing but p minus 1 into q, that is the thing but p, right, and that is a term which is common to both these terms, okay. That is term which is common to both these terms. So what I want to do is that I want to take that term to the left hand side, okay. I want to take that term to the left hand side, but what you can see is that that left hand side, that term is actually the same which is there in the bracket, okay. Whatever you have in the bracket, it is exactly the same thing that is here, okay, right. So suppose I divide by this term, that is where this earlier argument of assuming that everything is different from 0 comes into play. Essentially what it means is that I want to divide by this term, okay. I want to divide by this term, okay. So suppose I do that, then this will be, left hand side will be sigma j going from 1 to n mod xj plus yj to the power p, this whole thing raised to 1 minus 1 by q, right. That will be the left hand side after dividing, okay. And what will remain on the right hand side, it will be sigma mod xj to the power p, that is from this first term, okay, and then from the second term sigma j going from 1 to n mod yj to the power p whole to the power 1 by, okay, right. That follows simply by dividing by this term, okay, dividing by this term, okay. But again use the fact that this 1 minus 1 by q, that is the thing but 1 by p, okay, right. That is how we started with 1 by p plus 1 by q is equal to 1. So this 1 minus 1 by q, that is the thing but 1 by p, okay, alright. And using that you will get, this is the thing but what we are written here, right, okay. If you put 1 by p here, then that is the thing but the Minkowski's inequality, okay. So is it clear? So we have proved Minkowski's inequality, and what it means is that we have proved this inequality, that is norm of x plus y suffix p is less than or equal to norm x suffix p plus norm y suffix p, okay. In other words, this p norm is a norm on Rn, okay. P norm is a norm on Rn, okay, alright. Is it clear whatever we have done so far, okay, alright. Now there is just one or two extra points that we can see here, and they are the following. Instead of taking Rn, I could have also taken Cn, okay. Only difference there will be that the components will be ordered in tuples of complex numbers, okay. So for example, a typical point will be, suppose I call that point z, it will be of the form z1 z2 zn, okay, z1 z2 zn, and I can similarly define norm of this as follows, norm of z suffix p, see it will be sigma mod zj to the power p, j going from 1 to n, whole thing to the power 1 by p, okay, for 1 less than or equal to p less than infinity, okay, and if p is equal to infinity I will take maximum of mod zj, maximum over say mod zj for p equal to infinity, okay, that will define a norm on Cn, okay. Okay. So for each p, what we have seen, for each p 1 less than or equal to p less than or equal to infinity, this Rn with this norm suffix p, and similarly this Cn with norm suffix p, these are all norm linear spaces, okay, these are all norm linear spaces because this suffix p is a norm on each of these, okay, and since we have already seen that every norm linear space is a metric space, okay, all of these are metric spaces, okay. So we have got a big class, in fact infinitely many metric spaces by this, okay. In the next class what we will see is that not only for this Rn and Cn, we can also consider the spaces of sequences, they are called sequence spaces, and those can also be made into norm linear spaces by giving similar norms, okay. So for that again we shall require inequalities similar to this Minkowski's inequalities, but there the sum will go from 1 to infinity, okay, instead of taking a finite sums, we will need the sum going from 1 to infinity, and then the questions of convergence etc. will arise. But anyway you will see that whenever we want to talk about the convergence of a series, basically we have to say something about the partial sums, and partial sums are always the finite sums, okay. So basically using that idea we still use these inequalities to prove a similar inequality for infinite sequences, okay, and then we will use those things to prove something about the norms of the spaces of sequences, okay. That we shall do in the tomorrow's class, we will stop with this.